Good morning to everybody. Today is a pleasure for me to introduce you to Liberato Ferrata. He's an assistant professor in the Politecnico de Milano, and he was during some time for a postdoc stage in the Northwestern University, working with concrete. And now he is going to talk us about self-consolidating fiber reinforced concrete. He is a young researcher, but with very brilliant trajectory. He's part of the Rheology committee and also from the ETSI committee. And well, this is now time for you. Thank you very much to stay here with us.
Thank you very much. I am really very honored to be here this morning, and I want to thank you, Professor Jaime Galvez, for having invited me to give this talk. Actually, I will show you the results of, let us say, 3 or 4 years research. We are working on self-consolidating fiber reinforced concrete. And let us start from the very beginning, from the motivation which led us to study this kind of material. This is an example of a precast pre-stressed roof element. They are quite widespread all over the world, let us say, for roofs in industrial buildings. And we had a joint project some years ago with a company and with the Ministry of Higher Education in Italy related to the use of fibers in this kind of elements to completely replace steel roofs, so reinforcement versus shear and also versus transverse flexure, which can be a problem, while the longitudinal behavior is still guaranteed by pre-stressing tendons. Obviously, one of the key issues that you need to control in order to ensure the safe and reliable behavior of this kind of element when you remove steel roofs and put fibers is that fibers are very well, let us say, randomly or homogeneously dispersed inside of this element. Because if you have a spotty dispersion and you can have regions without fibers, because vibration, compaction can hinder this homogeneous dispersion, that spots may act as flows and may trigger the failure also for lower values of the ultimate load than you were able to calculate according to the design. And actually, we checked this issue with reference to continuous production. There were about 40 of those elements, and they were manufactured all along about 2 months of continuing production in a factory. And this was the transverse section of the elements. We picked up some cores in these 3 positions. The elements were cast from this side, and the concrete flowed here, and we had to put some more material on this side. So we took cores in these regions which were for us the most critical as far as fiber dispersion was dealt with. And we compared the solution with vibrated concrete and the solution with self-consolidating fiber reinforced concrete. And you can see here, these are X-ray pictures of the same core which was after cut into halves. This was the top part of the core. This was the bottom part. You can see that in the top part, due to vibration, you have almost no fiber at all. All the fibers were here, while these were with self-consolidating fiber reinforced concrete, which was with no vibration, and you can see that the suspension of the concrete, the fluid concrete, was able to hold the fibers in the right place. And also we checked the dispersion of the fibers in different positions along the axis of the element. Here they are just labeled with numbers, but these were about at half of the span, these at 1/4, and these at 3/4. And you can see with the vibrated concrete, the scatter of the content of the fibers, the cores were crushed after and the fibers were separated with a magnet, while you can see here the much reduced scatter when you have self-consolidating fiber reinforced concrete. So basically, this was a proof that with self-consolidating concrete, you can improve the dispersion of the fibers, and you can even orient them along the direction of the flow, and this would be beneficial for the performance. This is a prosecution of that investigation. This dealt with extracting some slab cores from the roof element and test them in 4-point bending, and you can see here the huge dispersion of the results with vibrated concrete, while they were much narrower dispersed with self-consolidating concrete. And this could be beneficial also for the design, for the characteristic value and the safety factor that you have to employ. So basically we decided to focus our research on self-consolidating steel fiber reinforced concrete, surely because we proved that there could be a better dispersion of the fibers and we don't have downward settlement of the fibers. We can reduce experimental scattering, so the statistical dispersion of material property. And after, there are the obvious benefits from self-consolidating concrete. We know that we have a more dense and a more compact matrix, so this could be beneficial for durability. Some authors claim that it's also beneficial for the bond between the fibers and the matrix. One of the most important things is that can we orient the fibers along the flow direction by suitably calibrating the viscosity of the fresh concrete? And so can we design the casting process target to the structural performance that we are going to anticipate? So basically, can we orient the fibers along the direction which will be the direction of the principal tensile stresses within the element when in service? Obviously, you can, combining the advantages from steel fiber reinforced concrete technology and self-consolidating concrete technology, you can increase the speed of construction, you can reduce the cost, you can reduce the crew sizes in a factory. The working environment would also better because you reduce the noise due to vibration. People involved in vibration do not suffer any longer of dead fingers and other blood diseases which are quite common. So there are some further benefits, some bonuses that you can add up and which are worthwhile to go on with this research. Basically, we approached the problem according what we call a holistic approach to the design of structures with self-consolidating fiber reinforced concrete, and there was a mutual interaction between the fresh state behavior, which we can control through a suitable mixed design procedure, the fiber dispersion, and the final influence on the physical and mechanical performance, and all these features contribute to the final performance of the structure we are going to design, also through the design of the processing and of the casting process. So basically we focused on these different aspects. First of all, we tried to assess a rational mixed design methodology for steel fiber reinforced self-consolidating concrete. After that, we looked into the issue correlating the fresh state performance with the fiber dispersion, and also developed some non-destructive methodologies to monitor the fiber dispersion in the structure, which can be useful for quality control when you go to the factories. After that, the mechanical properties as they correlate with the fiber dispersion and orientation as influenced by the fresh state performance and the casting process. And after that I will show you some results. I'm sorry, there were some nice movies, but they do not seem to work here. We focused on the shrinkage cracking because we are still working on these subjects. Okay, what about the mixed design methodology? Basically, we choose as a starting point a well-known, well-accepted mixed design method for SEC, which is the Rheology of paste model. The mixed design methodology was developed at Northwestern University, and basically it consists of these concepts. We have a densely packed assemblage of aggregates. We can consider them as spheres, and they have a certain void fraction. So we need a minimum amount of paste which is just necessary to fill the voids, and in that case we have a very dense, very stiff suspension. All the paste in excess is responsible for the fluidity, for the reformability, for the self-compactability of the concrete. And we assume this parameter here, which is the average spacing between the aggregates, you can compute it according to simple geometrical formula. This was a parameter, and you can see here we have it on the x-axis. Here on the y-axis there is an indicator of the rheological behavior of the cement paste. This is the ratio between the flow diameter as measured with the mini cone test and the viscosity. The viscosity actually here was measured with a rheometer, but actually this is a quite demanding test. If you want to go to a quality control in a factory, you cannot prescribe rheometer measurements all the day. So we are now working on alternative, let us say field-friendly methods. So how can we identify, for example, from time measurements from the slump flow or from the marsh cone, but I will not show this. Basically, what is the concept? The concept is that the more paste you add, so the larger is this aggregate spacing, and you need a lower value of this ratio, which means that you need a lower flow diameter, so a higher yield stress of the paste, and the higher viscosity, because the more dilute you make your suspension, and the most stiff must be the paste in order to guarantee your performance. While if you put a lower amount of paste, so this aggregate spacing parameter becomes lower, you need a more fluid and a less viscous paste in order to achieve the satisfactory performance in the fresh state. And you can see here the allowable zone is within this region. If you go here, you have a too fluid paste, so you have a too loose suspension, aggregates may settle down, may segregate. If you go lower, your deformability will be not satisfactorily, and you risk to have a too stiff concrete. So this was for plain concrete. We tried to extend it to fibers, and basically, which was the concept which we developed. These are some representative percentage of passing for aggregates, for the sand and the coarse aggregates that we use it to make our self-consolidating concrete. And we know that fibers actually are added as a fixed amount per cubic meters of concrete. So for example, 50 kilos per cubic meter, which is a quite common volume fraction of fibers. Actually, for those roof elements, we use that kind of element. We consider the fibers as an equivalent aggregate fraction, and we said fibers as 100% of passing to this diameter. We defined an equivalent diameter of the fibers, which is basically the diameter of the sphere which has the same lateral surface of the fibers. Because when the paste goes to lubricate the solid skeleton, basically it goes to envelop the solid particle. So the lateral surface was for us the key parameter dominating the problem, and this was easily computed with that formula. And basically after that we try to optimize our final grading curve, for example targeting to a theoretical curve which can be the Bolomey curve or any other kind of grading curve that you can use in usual concrete technology. And we developed the same design cart as for a plain concrete. You can see here we had some allowable concrete, some good concretes. Here we add some concretes which were too stiff, and here in this region, or also here, we had concretes which were too fluid and so prone to segregation. So this design cart was the same which we saw before for plain concrete, extended to steel fiber reinforced concrete, and mixed design methodology proved to be effective. After that, we went up to control the fiber dispersion. These data refer to the continuous manufacturing of roof elements I referred before. So you can see here, they dated back about 1 month and a half. And this was a simple control of the fibers in the fresh state. Pick up a sample from the batch, wash out the fibers, wipe them, dry them, and wait. And you can see that the target content is reasonably well guaranteed when you go in the batch. But you saw that when you go in the elements, you can have very wide variations. So, okay, we can use destructive methods to check the content of the fibers. The content from the batch in the fresh state is also desirable. You can also, from some elements from a continuing production in Italy, precast factory are forced to make every certain period of time a full-scale load test up to failure of their elements. So those elements could also be used for this kind of tests once they have been broken. But a very interesting thing would be to develop a method, non-destructive, which could be effectively implemented into the quality control procedures of the factory to regularly check the quality of the manufacts. X-rays can be good, but you need the equipment, and there are also some safety problems, health issues, because there are radiations. So we have worked and we are currently working on electrical methods, and also trying to see if thermal methods can be effective. I have some friends working on this subject, and we were speaking together with her before. Roberto Felicetti is working on that because he's an expert. But I will tell you about electrical methods basically. And the method was it's called an alternate current impedance spectroscopy. Basically, what is the concept? You apply to your material a certain difference of potentials. Basically 1 volt is enough. But this difference of potential is scaled along a certain range of frequency. You can see these numbers, 1, 2, 3, and so on. They are the logarithm of the frequency. So basically you go from hertz, 10 hertz, to megahertz. When you apply, look at this curve, when you apply to an unreinforced matrix, you basically see, and you know the difference of potential, and you measure the output current, amplitude, and phase, so you can calculate the imaginary and the real part of the impedance. When you apply it to an unreinforced or plain concrete, plain cement paste matrix, you get a curve like this, and this cusp represents the resistance of the concrete of the matrix. When you apply to a steel fiber reinforced composite, due to a very thin film which forms at the interface between the fibers and the matrix, under the low frequencies of the alternate current, the fibers behave as insulating, so they do not transmit current. And what you measure here, this cusp, is very close to the resistance of the concrete, of the unreinforced matrix. While under the high frequency of the current, you have that fibers are conductive, and so you measure the resistance of the fiber reinforced composite, which you can express those formula as a function of the volume of fibers and of the conductivity of the fibers. So basically, with only one measure, you pick up these two values and you can calculate the ratio between the resistance of the fiber reinforced composite, which is basically a function of the fibers, and the resistance of the matrix. And you can have information. This conductivity of the fibers is an intrinsic property of the fibers, just depend on their geometry. And you can have information about the effective volume of fibers in your volume sample of fiber reinforced material. This method was developed at Northwestern University by the group of Professor Mason and Professor Shah, Material Science Department. So we try to apply it to our purposes. It was applied by the same authors for some industrial scale application. This was a beam, a precast beam, so they made checks in different locations. And you can see here the results in one direction and in the other. So the flow of concrete was able to orient the fibers because you get differences. And here you can see some of the setup which was used. Basically, you have here the electrodes, and you need to guarantee the electrical contact with the specimen. In this case, they built up with a mortar, a small reservoir, and there was a sodium chloride solution to guarantee the electrical contact. We used a slightly different method I will show you. And this was to show that the matrix normalized conductivity that you can get from this method really matches with the orientation number of fibers that you can get from image analysis. This was the calibration of the method, which showed that the method is effective and we can trust them. So basically, this was a pre-work done at Northwestern University, which allowed us to go further with this method because we know that we could get reliable results. What we did, basically, we wanted to show the effectiveness of self-consolidating fiber reinforced concrete in dispersing homogeneously and in orienting the fibers along the flow direction. So basically, using the design card that I showed before, we designed 3 different mixes. One which was self-compacting here, one which needed vibration, and one which was prone to segregation. Actually, we did not go too far from here, otherwise we missed everything. So it was very, very fluid and prone to consolidation. And we cast some square slabs, 600 millimeters side and 60 millimeters thick. This was a reasonable compromise between the weight, because 2 of us must be able to lift it and to move in the lab, and the representativity. We wanted something for having the same sizes of the slabs of those precast elements which I showed you before. And this 60 millimeters is the average thickness of the slabs in those elements. So this was our reference. We used fibers 35 millimeters long, so there was surely a tendency to lie in the plane, and we neglected the true thickness measurements because the thickness was quite small compared to the length of the fibers. We cast 3 slabs with self-consolidating and segregating concrete, and we cast 2 from one side and the concrete flow in this direction, while 1 was cast from the center with an umbrella flow of concrete from the center. While for the vibrated concrete, we put the concrete in the center and we vibrated it for a couple of minutes until the complete filling. We first performed the non-destructive measurements for fiber dispersion, and after that, you see here, we cut 5 beams from here and we tested them in 4-point bending. This is the layout of the measures that we took with alternate current impedance spectroscopy method for fiber dispersion. Basically, we took the measures in 2 directions to check for the fiber orientation. And here you can see some of the results. On your right, you have the ratio between the resistance of the matrix and the resistance of the composite, which we know is an indicator of the effective content of the fibers in the cells in which we divided the specimen. You can see that with vibrated concrete, we have a very wide dispersion of the results. We range from 1.2 to 1.8, while with self-consolidating concrete, the results are much narrower. So it really means that fibers are well homogeneously distributed in the specimen. Oops. And this is the comparison for the same slab. These are the measures taken parallel to the casting, and on the other side you have the results of the measures taken transverse to the casting. So you can see that there is certain difference, and so the fibers tend preferentially to align along the direction of the flow. Here you can see when we use a very fluid concrete which is prone to consolidation, have in mind that the concrete was cast from here and flowed along this direction. You can see that you have a huge dispersion of results here, but as you go farther, the results become lower. So the fiber content becomes poorer and poorer because the concrete is not viscous enough to drive the fibers along the flow, and the fibers settle down just at the beginning of the flow. And after that, we went for check of mechanical properties. These are results from the PhD thesis of Stephen Grudemald. He compared conventional SFRC with self-consolidating, and these were beam specimens like the ones recommended by Rheology for testing toughness of fiber-reinforced composite. He really got a very huge difference in the mechanical performance. So he went to check the basic mechanism. He made single fiber pull-out tests in a conventional matrix and in a self-consolidating concrete matrix, and he obtained those results. So really it seems that it's not the bond between conventional concrete and fibers, or self-consolidating concrete and fibers, to be the real reason which justifies the bad performance. One of the reasons may rightly be the better dispersion and the preferred orientation along the flow. If you cast a beam, the fibers tend to orient along the beam axis, which is the direction of the tensile stresses when you go for testing, and you can have this. And we made some similar tests on the specimen that I showed you before. You can see here, these are the results for vibrated concrete. These 3 beams come from the same slab. They were 1, 2, 3 beams. And this one was tested upside down to casting. So in a vibrated concrete, due to the vibration, the fiber settled down, and when you test upside down, you don't have. And these are the results for self-consolidating concrete. They are very narrow dispersion, and there is practically no significant segregation. You cannot avoid some settlement because the fibers have a specific weight which is about 3 times that of the suspending fluid matrix, but they were quite able to hold in suspension. So after that, we went for a structural application. Actually, this was not conventional self-consolidating steel fiber reinforced concrete, but was a ultra high or high performance fiber reinforced concrete. And the problem which was asked us to solve was this. This is another kind of roof element quite commonly manufactured by a precast factory. This has an inverted Y shape, and this one is because the company wants to have the flat ceiling in the factory. And they complete it with these slabs which span about 2 meters, 2.5 meters. And actually the traditional solution, the thickness of the slab is 80 millimeters nominal thickness, because you have to respect the minimum thickness on both sides, and you have to place some reinforcement here on the tension side. So due to these constraints, you cannot go lower than 80 millimeters. We designed a solution with only ultra-high performance fiber reinforced concrete, so no conventional reinforcement. We could go down to a nominal thickness of 25 millimeters. Actually, the results of a production test was about between 25 and 30 millimeters. So, but still there is a very good advantage, because basically go to 1/3 of the thickness, and you surely have a very much lower self-weight, which also means that you can better design your supporting structure. You probably need a lower capacity crane for construction. So there are several benefits. And also you can easily couple, for example, the interior beam with some insulating layer which can improve the energy efficiency of the building, or can be, for example, a textile layer which could be good for fire resistance and so on. So you can end up with higher end solution, simply not related to the structural performance but to the overall performance of the building. We also went for the steps. So first of all, we went through the mixed design of this material. Actually, we had a very small diameter here, 2 millimeters, because the maximum fiber length was 13 millimeters. They were short fibers. We had 100 kilos of fibers because we wanted ultra high performance, and here is the mixed design we ended up. Basically, we optimized the rheology of the paste, of the mortar, and of the fiber reinforced mortar with very simple tests, the mini-cone slump flow and the marsh cone tests. And after that, we also checked, with reference to small scale specimen, what we call the fiber dispersing ability. For example, from the petty of the mini-cone flow test, we divided it into sectors, and after that washed the fibers and weighed them, and checked how many fibers were in the center and how many fibers were in the outer ring, because that was an indicator of the tendency of fibers to settle down. Or we simply cast a small beam here, and after that dividing into 4 sectors and check the weight of fibers in each one. And you can see here that the results, okay, there is some difference, obviously. You cannot end up with 100, 100, 100, but the dispersion was satisfactory for our purposes. We also performed the tests in the factory using the usual tools that are used for self-consolidating concrete, but actually for this kind of material, these are not very representative in our opinion. You end up with a slump flow diameter of more than 75 centimeters, surely. The passing ability is absolutely guaranteed because fibers are small. You don't need to modify the gaps here for longer fibers you should need probably. And the V funnel was a little bit high, so this was a very viscous matrix, but we had to design it in order to guarantee that fibers were able to be driven by the concrete flow. And we, before casting the slabs, you will see later, we casted some, okay, not very small, they are 0.5 meter by 1 meter slabs, and we casted them in 2 different ways. This one and the red lines are the flow lines of the concrete, and this one, so we had an almost radial flow of concrete. And after that we cut the beams, as you see here. Some of them were cut with their axis transverse to the flow, and some of them were cut with the axis parallel to the flow. Here you have the cube compressive strength of that concrete, and here the setup of the 4-point bending test for this kind of specimens. And okay, and you can see some of the results that we got. I don't know if the X-ray pictures are quite clear, but you can see here these slabs were cut with their axis parallel to the flow. There is a very grayish network of the fibers which are aligned in that direction, and you can see here the performance of the 2 beams. This beam L3 was always tested upside down, so there was still some problem of segregation of the fibers, but the difference was acceptable. And these other beams were cut with their axis. This was the direction of the flow, so the fibers were perpendicular to the tensile stresses. You can see the huge difference in the performance. Here basically we got a conventional self-consolidating fiber reinforced concrete. We have a first cracking. After we have a remarkable toughness, but there is no hardening post-cracking behavior. While here we have a significant hardening behavior with multi-cracks. You can see here in the X-rays picture, you can see some blacker lines which show the multi-cracks which formed before the peak, and we could hear. We did not perform acoustic emissions, but we could hear during the test these multi-cracks forming. And after that, we had the localization into a major cracks, and the softening behavior started. While here, we just have one major crack in the beginning, and that one went on without the formation of any other crack. When we cast okay, this is just a comment we already saw. So basically the fibers were effectively oriented. This remarkable difference could not be justified. And there is still some effect of downward settlement, which we are working on to improve the mix design to better check also that, because we want to go further with some other kind of elements, for example, curved elements or ribbed elements, and in that case the downward segregation is much more important than in this case of very thin elements, and most of all, if they work in the same direction as you cast, the downward settlement could not be a problem, could be only beneficial. This is the result. These are the results when you cast in the radial direction. You still have some difference. These were parallel to the casting, these were transverse to the casting. There is still some difference, but not as huge as in that direction, probably because in this case the orientation is more random, less preferential like in the case before. And we checked this with a very detailed analysis. Actually, this analysis was performed at Boğaziçi University in Istanbul in cooperation with Dr. Özgürt, who spent some time with us at Politecnico. This is the cross-section of one of the specimens, and we divided it into a network of cells. These were 3 millimeters by 3 millimeters, and some micrographs were taken. You can see there an example. And from the elliptical shape of the fiber cross-section, we were able to calculate the cosinus of the orientation angle. And basically we ended up, through a statistical method in the paper we submitted to Materials and Structure, there are the details of the method, we ended up with calculating orientation density values in this direction, in this direction, and in this direction. And you can see that for this beam here, this specimen here, which is basically this one, we have an orientation factor of 0.634, which is basically responsible of the mechanical performance. While in this case, the orientation factor which is responsible of the mechanical performance is this one. So basically we have a ratio, it's a little bit lower than 3, which more or less coincides with the ratio between the maximum loads that we measured. So there is almost a direct proportion between the orientation of the fibers, or the number of fibers effectively oriented in the direction of the principal tensile stress, and the mechanical performance that we measure. And the same is in this case, where you can see here we have in this case a 0.539 and the 0.398 in that direction. So the difference in this case is much lower, and is the reason for which the performance is not that different like in the case before. We are currently working now on the identification of the properties, of the relevant mechanical properties for the design. We had good results for the material, for the design of the casting process. Now we want to propose a design methodology with this kind of material. And due to the behavior that we had a pre-peak multi-cracking stage and a post-peak unstable crack propagation. So we proposed a pre-peak stress strain low, because in that case we have a continuous material, and the post-peak stress crack opening low, as is common for this kind of materials. And these are the details. This is basically for the matrix. This is the peak load, and this beta factor is related to the fact that we are in bending, so it's like in the model code. While for the post-cracking low, we started with the actual proposal of the Italian guidelines on the design of steel fiber reinforced concrete element. Actually, we have several guidelines in Europe. There are RILEM, which have been accepted as an EN standard, and they prescribe a notched beam specimen in 3-point bending. We have in Italy a notched beam specimen in 4-point bending, a little bit different. But those specimens are 150 millimeters deep, and there is a notch which triggers the fracture in one section. When you go with this kind of application, very thin slabs, the notched beam specimen is not absolutely representative of what would happen. So in our guidelines, and is going to be accepted also in the new version of the model code, they speak about a structural specimen. So a specimen which actually reproduces the structural element to be manufactured. So the specimen, the specimen must be as thin as the element to be manufactured, and it is prescribed to check for 2 different levels of crack opening. This one is 4 times the first cracking strength. It has to be renormalized with respect to the peak, but I don't go into the details. And this one is for the ultimate limit state. So it's prescribed to take the ultimate limit state crack opening at 2% of the specimen depth. But actually, for this kind of elements, 30 millimeters or 25 millimeters thin, 2% means 500 microns, 600 microns, so still a very limited crack opening range. And if you go with this kind of identification rule, you see that you get this very steep decrease. This is the peak, this is the serviceability limit state, this is the ultimate limit state, and if you extrapolate this, you go rapidly to 0. And even if we didn't perform the inverse analysis, you can easily imagine that this is not good for the performance that we got. So we proposed a much more, not cumbersome, but with some other points, not limited to 2% of the specimen depth, but up to 10% of the specimen depth, just to add a further point. And this softening behavior seems much more reliable for the material that we got, both in the case of fibers parallel to the tensile stress as in the case of fibers transverse to it. And we have now a project ongoing which exactly deals with testing the reliability of this identification procedure for the materials we proposed. And here basically is the same thing for the other specimen tested with the different casting process. The final goal will be to check the performance of the full-scale structural elements. The elements were 1 meter and 20 centimeters wide and 2 meters and a half long, and there are the details of the testing instruments which we placed, and here you can see the elements under testing. You can see there the remarkable ductility of that element under the loads, and this is the performance, which also show these were cast with some control of the direction of casting. These were cast randomly. So what we observed at the scale of the small specimen also reflects to the full-scale element. You have a higher capacity, but most of all, you have a higher ductility here in the mid-span section compared to this case, which was cast from the center and allowed to spread radially. We also I am very pleased to talk about this work because a student from this university, Esther Bermejo, spent some time at our university last year, and we worked together on this project. It deals with the durability, let's say durability in a broad sense, of this kind of material. So basically, these elements are taught for roofings, and if you think you had to always to place some waterproofing layers in order to prevent water to leak inside. But since we are dealing with a very dense, very compact matrix, can we think that this material is automatically waterproof, so water cannot go inside? You can have some cracks due to autogenous shrinkage, for example, which surely you do not control in the precast factory. You can have some small cracks due to thermal strains, but is the material able, due to the normal wet and dry cycles in the season, is the material able to self-heal back these cracks? So basically what we did, we started with this kind of investigation. We picked up some specimen and pre-crack some of them, inducing a crack opening of 400 microns. And you can see here the pictures at the microscope, the cracks where they were not visible at naked eye, but when you go with microscope you can see them. We put them in a climate chamber and performed these cycles. They were representative of a typical winter condition, day and night in Italy climate. We have 20 degrees you can have, with a very high relative humidity. It simulates the fact that it has rained and there is some layer of water there. And after that, this water, when in the night you go down, freezes and may penetrate in the cracks and cause the expansion. So we performed several groups of cycles, 25 as is written there, 50 and up to 125 cycles. And after each group of 25 cycles, we had both pre-cracked and uncracked specimens. We picked up groups of 3 specimens out of the chamber, performed ultrasound test measures and 4-point bending tests. And we are just going to look into the results. You can see here that for both non-pre-cracked and pre-cracked specimen with the number of cycles, this is the stiffness measured in the ascending branch of the load deflection curve during the 4-point bending test. There is a clear progressive recovery of the stiffness. And the same tendency you get for the peak strength and you get for the post-cracking equivalent strength. So it really seems that these cracks, due to the water that we supplied during these hygrothermal cycles, the water was able to penetrate into these cracks. And since the starting water binder ratio was very low, was 0.18, there was a lot of unhydrated, this was our hypothesis, which obviously we are currently working on, but there was a lot of unhydrated material which was able to further hydrate and to close back or fill the cracks so that the material was able to refill, to gain again the previous properties. Just to conclude, these are some results about the effectiveness of fibers to control shrinkage cracking in self-consolidating concrete. We know that this is a problem because in self-consolidating concrete you use a larger amount of paste, a larger amount of cement or binders, and shrinkage but also creep, for example, can be the problem to design. You generally don't have problem of strength. And these tests were performed when I was at Northwestern University, and I worked together with Dr. Kwon, which is now assistant professor in some university in South Korea. I don't remember exactly the name. We performed the classical ring tests. We used both polypropylene and steel fibers. And besides the test, Dr. Kwon developed a model, which was a very comprehensive model, basic to predict shrinkage, so taking into account the type and the geometry of the fibers, the internal and external restraint, which can cause stresses to be developed due to shrinkage, the mechanism of shrinkage due to basic diffusion, the interaction between shrinkage and creep, which can reduce the cracking due to shrinkage, and to take into account the cracking resistance of concrete, we use the classical smeared crack approach as conventionally in fracture mechanics. And here you have some of the details of the model. You have here the internal restraint due to the gradient of humidity distribution, and you can also have external restraint which forbid the free deformation due to shrinkage and cause cracking. This is the interaction with basic creep and drying creep. We took the Bajan theory for this one. And this is the classical approach for fracture mechanics of concrete, the fracture energy, and we embedded the effect of fibers with the stress-slip, tangential stress-slip curve. Actually, in modeling with finite elements the concrete annulus around the steel ring, and in order to trigger the failure, if you use axisymmetry condition, without this randomness of tensile strength distribution, we don't have a crack in starting in one point. So we have to assign the material property according to a statistical distribution. There was an average value and there was a fluctuation of 10%, so that we could have values between 0.95 and 1.05, the target tensile strength, and in the lower zone we had the fracture starting. I'm sorry that this movie do not work, but this was just to show the effect of moisture distribution. And in the case of plain SEC, we had one major crack starting and propagation, while with fiber reinforced SEC we had several cracks. So the amount of the crack opening was reduced because it was distributed along a bigger number of cracks. But you can see here the results that we got. This is the plain matrix for polypropylene fibers. This is the plain matrix for steel fibers. They were different because of the different geometrical properties of the fibers. And you can see both with polypropylene, but most of all with steel, which are more effective, probably they have a better bond and the final hook is better, you have a great improvement in the performance. The age of first cracking is surely delayed, but the amount of crack opening, final crack opening, is dramatically reduced, which is surely beneficial. Also taking into account what we previously said for self-healing, because these cracks you cannot surely self-heal because too high. But cracks up to 5 microns, you can hope that the material will be able to self-heal with the development of delayed hydration products. And the model was well able to capture also the strain in the steel annulus, which was the control to check when the crack starting. You can see here with the matrix at a certain point the strain in steel annulus decrease. When the crack is formed, there is no effect of confinement. With polypropylene fibers you have a decrease, but the steel always remain active, while you can see here with the steel fibers the effect always remains because the crack opening is still very small. So I am arrived to the conclusions. Basically, we started and we are going with this research on self-consolidating steel fiber reinforced concrete, which is a material which is suitable for high-end structural application. Surely it combines the traditional benefits which we all know of the SCC technology and of the steel fiber reinforced concrete technology. But we can have further bonuses, so we start with what you know that is good for SCC, what you know that is good for FRC, but you can have reduced experimental scattering, and most of all, you can really tailor the material performance and the casting process, this is very important, to orient the fibers along what you anticipate will be the principal stress direction of the element when in service, and you will optimize your structural performance. And this field, a very cutting edge topic, is the numerical prediction, numerical simulation with computational fluid dynamics of the fluid concrete behavior, because through that you can really have the orientation of the flow lines and predict the orientation of the fibers. Also, you can enhance the durability and you can check and improve the self-healing capacity of the material. The implementation of this kind of material into industrial production needs basically a dedicated quality control procedure, a dedicated mixed design methodology, dedicated identification test, because what is currently recommended for conventional steel fiber reinforced concrete or conventional XCC may not be suitable depending on the specific kind of material and on the specific kind of application that you want to design. One thing that you have to measure in the fresh state is how effective the material to disperse the fibers or to orient them, and also the research on non-destructive methods to measure the fiber dispersion and orientation is worthwhile being performed, because that is a crucial topic for the implementation into the industrial production, as well as the measurement of the ardenate state properties as correlated to the casting procedure and to the thus obtained fiber dispersion and orientation. Basically, these all will form the subject on which a very newly established FIB task group 8.8 design with tightly flowbore concrete will work. We just had the inauguration meeting at the end of April in Ghent, so the committee will last 4 years, and we have people from all over Europe and some overseas corresponding members. We will try to develop some guidelines including all these aspects to design structural elements with tightly flowable plain and fiber reinforced concrete. And I thank you for your attention once again.
Thank you very much for this very nice talk.
Thank you.
We have time for some questions.
Yeah. You started with a very modest objective aim, which was to improve the shear resistance of the roofs, and after that you have evolved to
higher and higher,
something called ultra high performance. So, in your opinion, what is? Well, of course, it depends on the application, but in your opinion, which dosification or which kind of compressive or level of concrete compressive resistance is the best in terms of economical for precast?
Oh, actually, as you said before, it depends on the application that you are going to design, because that case, basically the compressive strength was most of all a side result because we wanted high performance in bending, so that was. For the conventional elements, 50 or 60 Newton per square millimeters is okay because you don't require more. Actually, any kind of self-compacting or self-consolidating concrete has probably in the past years this problem. You design it for the first state performance and you end up with a strength which can be higher than you need exactly. But now the research, and it has been proven that it's feasible, is going towards a more economical SCC, so you can produce SCC also for 30 Newton per square millimeters if your application don't requires more than that. With this kind of application with fibers, what dominates probably is the toughness that you require in bending, and so the compressive strength is basically some side results. It can be higher, but you check the toughness, so that is your target. And in that kind of ultra high performance, we want about 10 to 15 first cracking and up to 20 and even more ultimate load capacity. So that was what dominates our mixed design, and the 116 in cubic strength was side activity. Another kind of application for this kind of high performance composite could be in joints in precast structures. If you have to for seismic resistance, if you have to design a joint and comply with the Eurocode 8 requirements, probably you end up with a reinforcement that you are not able to put there. And so even with self-consolidating concrete, you could have difficulty in realizing that joint. So those fiber composite, they may be conventional fiber, they may be ultra high performance, can greatly help in reducing the congestion of the reinforcement, and you can end up with a joint which works. And in that case, your strength requirement should also take into account, for example, the capacity design rules. So you want some kind of behavior, overall behavior in the structure, and so your joint should be designed for that overall behavior. So basically the compressive strength really is something that fits to the specific application that you have to design.
I mentioned the compressive strength.
Yeah. That is what any kind of structural engineers has always in mind. What is the compressive strength I have to design for? But this kind of material really requires the performance to be thought in a more holistic, as we said before, a more comprehensive way. So surely that is what we require, that is what we have to prescribe, but it's not the unique thing. And in this kind of materials, probably the effort should be done to prescribe the performance in a much more multifold way, because sometimes the compressive strength may be required by the rule, by the codes, but may be meaningless. In this kind of application, the compressive strength more or less was absolutely. Because if you design those elements, you are always in the compressive region, you are always in the elastic range, because that material is elastic up to 60 megapascal, so that's not a problem.
Yeah, I was talking about the compressive stress, but it was related, of course, to the tensile stress. And to the fact that we have self-healing. And we can improve also the serviceability.
Sure. That is another important aspect, that, for example, with those if the fibers are, I did not show you here, but if the fibers are well oriented, you can have the same crack opening for a much lower deflection. Deflection is typically the parameter you check for serviceability. So if you can limit the deflection, you also improve the serviceability, because your slabs, for example, do not sag too much, and that is another aspect. So the performance are really very strongly intercorrelated, and you have to take into account all of them for a true and reliable design and prescription. Sure.
Other questions?
Yes, thank you very much for the very extensive presentation of your experience and your results. It has been very, very clear, I think.
Thank you.
Even for people like me, that sometimes it's difficult to follow all the mechanical performance of the materials. I'm more specialist in the material itself. And I would like to ask you about the non-destructive techniques, in particular impedance spectroscopy. I think it's a very interesting technique. I have used a lot in corrosion, for corrosion. At which age would you perform your
Basically, we performed those tests. The labs were about 45 days age, but not me directly, but Dr. Rosur performed also some tests on fresh specimens, and the method was effective. So you can also, with a suitable test setup, you can also perform some tests in the fresh state. The problem is that when your elements cast, even if you go in the fresh state and got bad results, what you do with that element. So that was, we have been asked by the company. Should we throw it away in some way? But by the way, the methodology is effective also in the fresh state, and in the fresh state could be, for example, used if you need to calibrate a casting process or something like that on small mock-ups, and that is while in the hard-net state. Even at one day, for example, in the precast factory, you can think of performing those tests just after the pre-stressing release and the thermal cycles have been over, before your elements are delivered somewhere. But by the way, it's effective also at a few minutes of life, in a sense.
I can imagine you have employed high impedance spectroscopy, and in impedance what is really difficult is to get the interpretation of the spectra.
Yeah.
Because probably there is a lot of information behind it.
Yeah.
But I could see you have determined the resistivity. Finally,
Yeah.
is the parameter.
Yeah.
Have you tried to obtain the same parameter from another more direct technique?
We are currently working on that with more simple methods to just correlate it, because as you say, impedance may be a very dedicated, very refined technique, and also in many cases you need a dedicated equipment which can be costly and so on. So it's a work we are currently doing with our Department of Electrical Engineering. We are trying to go deeper into this technique and more broadly into electrical methods, also trying to see if there can be some simple measure which can be done in a more routinely way and using impedance for more refined checks. Yeah.
And have you noticed, I don't know if you carry out the different type of testing, varying the orientation, the casting and the resistivity you are measuring.
Yeah.
Do you notice difference when you have fibers or not?
I did the test in two directions according to the casting, and these were the difference with fibers. So I was able to get some differences for the fiber orientation. That was the only information that I have about the casting direction and orientation of the fibers, and it seems to reasonably capture. And after that, we tried to match these results with the annual counting of the fibers with the orientation. And yeah, it's something which can be, you can see here, this is an orientation parameter. Basically is a fractional directional conductivity. You weight the conductivity or resistivity in each direction to the sum of the three directions, and you compare with the orientation number, and there seems to be a good correlation, which was a proof of the reliability of the methodology. At least they interpreted in this way.
I have one more. It's correlated with durability.
Yeah.
You said that the use of fibers and self-compacted concrete enhance durability. However, your tests are concentrated in one specific.
Yeah, sure.
So it's freeze and thaw, and you find certain, we can say, I don't know if improvement, because I'm sure there is actual healing, but I do not agree with your mechanism.
Yeah.
That is another thing.
Yeah.
But at least my experience with this type of concrete, with the fiber self-compacted concrete and durability, is that the transport of fibers is not significantly influenced by the presence of the fiber.
Yeah. Basically, I can agree with you. I'm not an expert in this field, but what we are aiming to prove is that simply the fibers, since they help in reducing the final crack width, they can reduce the penetration, and they can guarantee some better self-healing than in the case. That is what our final goal is, not about transport mechanism. I agree with you that fibers do not affect that very much. That is a problem related with metal. Yeah. Yeah, I repeat, I'm not an expert. These were our first results, and we wanted to check that with this specific application. We are now performing some summer cycles, so with temperature up to 60, 65 degrees to see if this can be confirmed. But that was basically related to how much is effective in keeping narrow the crack widths, and how that narrow crack widths can be self-healed by the supply of extra water. So that does not deal with more fundamental durability aspects.
Thank you very much.
Okay.